Welcome to another AQA. I was about to say AQA AS chemistry video. It's an AQA A-Level Chemistry video now because we now finished all of AS chemistry. I will be uploading videos on the channel based off of exam questions for year 1 inorganic, and I'm obviously going through them. But yeah, so I'm going to organic chemistry now. I actually did up this topic. So this topic is on the one I'm doing today is I'm starting organic chemistry year 2. I actually did this video. It was one of the first videos I done. But it was like half an hour long. It wasn't in depth. It was a very good video, but it was so I wouldn't say actually it wasn't a good video. I wasn't confident at all. But if you want to check that out, kind of go through the points there. I did that already, but I want to try and do this video again, and do it in a much less time and probably in a much more, I'd say, with a better performance than last time. Alright, so let me stop talking and just get straight into it. So, optical isomerism is a form of stereoisomerism, and optical isomers, they're also called enantiomers and are non-superimposable images of one another. So all they are is that they're just mirror images of one another, and yeah, so non-superimposable mirror images. So you're probably thinking, why have I done this? This is a outline of my hand. I had done it. This took a bit of time because I called mistakes, but I also have to shrink it down a little bit so it fits on the page. But the reason I've done that is because it represents your hands are examples of non-super mirror images. It's a perfect example that's always shown. Like much like your left hand and your right hand, some molecules have mirror images, and these mirror images are non-superimposable upon each other. This means that they have a different spatial, I won't say spatial structure, I say spatial arrangement. They have a different spatial arrangement. So no matter how much you twist your hands, you can't make a left hand into a right hand. You can't really do that, right? So the idea of you understanding from this is that the idea of stereoisomers in general are a stereoisomer is a molecule with the same structural formula but different spatial arrangement of atoms in space. Same structural formula but different arrangement of atoms in space. And as an optical isomer is just a stereoisomer, so a different arrangement, same structural formula but different arrangement of atoms in space, but it produces a chiral compound forming two enantiomers that have non-superimposable images of each other. Did I get a definition of it? No, I didn't have a definition of it, but I think it's pretty obvious what it is. It's a stereoisomer, so the definition of a stereoisomer, because it is a form of stereoisomerism, but in particular in this case, it has a chiral center, because remember there's two types of stereoisomers. There's EZ, cis and trans stereoisomerism, and then it's optical isomerism. What's special about optical isomerism is that they have a chiral center. As I'll go through what chiral center is, and and all it does is that when you have a chiral center, you can definitely produce two optical isomerisms that have non-superimposable mirror images. Think of a mirror, right? If I had to mirror this image here, right? These are mirror images, same structure, but the arrangement of my fingers and hands are different. It's not the same. They mirror one another. Same general structure, but the arrangement is different. Alright, I'll stop talking now. Chiral center, right? Molecules that have 4 different groups bonded to one carbon atom have 2 mirror images which aren't superimposable. The carbon atom with 4 different attached groups is called a chiral center. Chiral centers lead to chirality in molecules. So I'll give you an example here, right? If you have a molecule with 4 different substituent groups bonded to one carbon atom, I think it can be with other atoms as well, but carbon is the only one that genuinely only forms 4. But I think the rule can be applied to other atoms. If I'm wrong, I'm wrong. But just say carbon in an exam. That's the best way of saying it. This is coming from Seneca, so it's just an atom that has 4 different substituent groups bonded to it. So you can see here, one is a hydroxyl group, one is a methyl group, one is a a fluorine bond or fluorine group, and one is a nitrile. The name of this molecule, I've literally no idea. I can guess it. 2 hydroxy propanitrile. Yes, 2 hydroxy propanitrile. Yeah. Anyway, the name's not important, right? But the idea that you can see here that this central carbon that has the little asterisk here is bonded to 4 different substituent groups. If it's free, it's not and that makes this carbon atom here a chiral center. This carbon atom here as bonded to these 4 different substituent groups is called a chiral center, and therefore this molecule is considered to be chiral. If it was 3, it wouldn't be considered chiral. If it was 2 different groups, no, it has to have all 4 bonds are different, right? So why it's important to know it's also important to know how to draw chiral centers. Remember that these atoms these molecules are 3D. They're not just some of them are you can imagine them as 2D. Some of them you can actually imagine as 2D, but for a chiral center, definitely not chiral center. Any chiral molecule, there's some molecules are literally symmetrical, and are straight or linear, I should say. As I said, I've shown you videos of when I did linear compounds, right? But chiral centers are usually, you can say, for example, tetrahedral, right? That's something that might be in a tetrahedral shape. The idea is that you need to understand that they're 3D, right? They're 3D. I don't want to kind of model your head around about what shape is what, but the idea is that they're 3D in shape, and you need to be able to know how to draw them. Now, it doesn't require you to have some sort of crazy artistic design. All you need to know is how to draw the bonds to represent a particular type of orientation, right? So what I mean by this, look, so in an example, this is a tetrahedral compound, right? But it's not 2D. This is obviously in 3D shape. There's an atom going above the bond, then there's maybe some that are on the same plane, and there's maybe one that's going behind, and that's to show. Obviously, it's not very difficult to kind of draw this. It isn't really difficult in this case, but like to do all of this to show that it's what the 3D shape is would be nice. But there's a much easier way that you can represent 3D shape, and that's by drawing the right type of bonds to represent that compound. So, for example, if we have a bond that's going behind the plane, we can represent by dashed lines. So dashed bonds indicate an atom below the plane of paper, right? So I've got couple examples here, right? So if we're representing this one here kind of represents a bond that's going behind the plane. So think of it like this, right? So say this is like one plane, right? And then I had this kind of like, and I know this is the best example, but this kind of highlighter here that represents a bond that's going to an atom that's below the plane. We'd use a dashed line like so. We'd use a dashed line like this to show that the bond is going below the plane, right? This isn't all. This is a way of your examiner understanding that you know that this compound is a 3D shape, and they're not all on the same plane. So this atom is actually going downwards, or if you were to represent this by a 3D bond, it would be going behind or underneath the page, as the technical term is used. And then if it's going a thick wedged bond, it would be going above the plane. So if you're thinking about an atom that's going above the plane, so say this is the plane, this little bond here, this little upwards bond here that's going above the plane, that will be represented by a wedged bond, or represented like this, right? So if it's going above the plane, right, say it's a carbon atom here, sometimes it's colored in, sometimes it's not colored in, but it doesn't actually matter if it's whether or not it's colored in or not. The idea is that you understand it's a wedge line, right? Try and do a better example than me here, but I usually color them in. There, anyway. There, that's showing that the bond's going above the plane. If it's going below the plane, there. And if they're on the same plane, you can use the normal lines that you use to represent a covalent bond, right? Okay, so how am I gonna, and then, yeah, so different optical isomers of, I've used bromo here. So different optical isomers of bromo hydroxy acetonitrile are above, or I should say above, this should be below. I mean, I did just copy this straight from Seneca, some of these things. So, right. So if I try to rotate these two, these are exactly this. These compounds are optical isomers of one another, right? The optical isomers of one another, right? So the same. You can clearly see they have the same structural formula, but their atoms are arranged differently in space. So if I had, it's so weird. I can't really show you an example of what I'm trying to say here. But the only way I can actually really show you is with my hands, right? Say this is the one enantiomer. This is the compound, right? This is the shape of the compound, right? The mirror image would be like this, right? I can't. They have the same structure and they look exactly the same, but in reality, if I was to put one over another, it doesn't matter how many ways I keep on twisting it, I can't make this the same as this. I can't physically move my thumb here and my fingers in a way that makes my right hand a left hand, and that's kind of like the same principle that's going on here, right? I wish I had like a Molly model equipment or something I could just show you, but for this compound here, this isn't a this clearly isn't a chiral compound, right? This obviously isn't. It has four of the same different groups. So four of the same groups attached to one carbon atom, right? But it's understanding that this here, they're oriented, they're flipped, but they're not just flipped in a sense that they can be flipped back. They're permanently flipped in this way so that they can show you that they're actually different compounds. All right, so drawing enantiomers, right? So you have to be able to be able to draw enantiomers for chiral molecules. So for step one, right? So you get a question where they want you to show. They'll ask you a question. They'll tell you a question like, can you draw out this structure? Or in fact, what they'll usually tell you is that they'll tell you to do a mechanism for a reaction, right? Or they'll just say, what's the product of this reaction with whatever and whatever, and you'll find out that once you've done that reaction, it'll probably be some sort of a nucleophilic addition elimination or something like that, and eventually you might get in a position where you find yourself that you have a chiral compound, right? So once you've drawn the chiral compound out, the first thing is you want to find the chiral center. So step one, if you want to draw, if they ever ask you to show that this is what type of isomerism this is, and draw the two examples of that type of stereoisomer, this the first thing you do is you find the chiral center. The chiral center is at the carbon atom which is bonded to four different atoms or groups of atoms. The molecule shown above, below. There you go. I did just copy it. I have no shame. The molecule shown below has a chiral center at the carbon atom, which is circled. So if I was looking at this is a carbon atom, right? This is a carbon atom, but is it bonded to four different substituents? This is a skeletal structure, but look here, right? This is one different substituent, fine. This is one different substituent, fine. But here I would have hydrogen. Remember, this would be a hydrogen, right? I'd have a hydrogen here, I have a hydrogen here. It can't be this one, it can't be that one, because it's hydrogen here, hydrogen here. It can't be that one, right? Because that's just really two here. It only has two. This is only one. Does this have four different substituents? One different substituent, two different substituents, three different substituents, four different substituents. That must be the chiral center. So, and if you then once you've done that, you draw one enantiomer. So draw the four different atoms or groups of atoms in any order around the chiral center. Remember to have the wedge line showing the bonds that's coming out of the paper, dotted lines shows the bonds that's going beneath the paper, and normal filled lines showing the bonds that are on the same plane of the paper. So I want you to pause the video now and actually try and draw this compound out as an enantiomer. Just draw this one out as using what I've just said before. Alright, I assume that you've unpaused the video now and you try to draw that out. So how would I draw that out? As draw it out as saying, now I'm going to do it on this one side here, but I'll just draw it out. Have I got another? Yeah, I've got another space there. So if I was to draw this out for the sake of this, you usually draw on one side. I'll show you why I should draw on one side. I'm drawing it in the middle here for the sake of drawing it in the middle so you can clearly see, but you usually draw it on one side and I'll explain why. But I'm going to do it. So carbon atom here, there's a hydrogen atom. Can I represent this hydrogen atom in any other way? No, I want to represent it in this way. So this hydrogen atom is going above the plane, right? It doesn't necessarily matter which ones you showed that are going above the plane, and you don't need to know which one is going above the plane or below the plane. Remember, this is an atom in space, so it will constantly be rotating itself in space. This pencil here will constantly rotate in space, no matter. So this will be the top part at some point, and at some point this could be the top point. We just use reference points, but realistically, it doesn't really matter which one you choose. It could be the hydrogen, it could be the chloro group, but just showing that you know it's that you have the idea that it's got in space at some point. One will be the top, one will be the bottom. So that hydrogen is going to be the top. Or it's going above the plane. I'm gonna draw the chloro as going. How am I gonna represent this chloro? I'm gonna represent the chlorine is going below the plane here. The chlorine is going straight. The chlorine is on the same plane as this group here. I've decided to do it on the same. So this is all on the same plane, right? And then this would be CH2OH. And then now I've decided to go and have one group here. And this is going below the plane. And this is my cyanide group. Now I've done it here so you can all clearly see it. But the reason why you should do it to one side, because when you draw the enantiomer, you maybe need to show the mirror image of this, right? So draw a dotted line on the right of the first enantiomer. So I usually put this to the left. So draw them, and then once you've drawn the dotted line to the right of the first enantiomer, draw the mirror image on the other side of the dotted line, and you should now have two molecules on either side of the dotted line, and the two molecules will be non-superimposable images, and they are enantiomers of each other. So can I just do this quickly? Let me see if I can actually. No, I can't take it out. You know what? I can just move it here. Yeah, I'm not gonna do another one here. Yeah, I have more space there, but I can just push this up actually. Right. Okay. So I can once you've done that, the last thing you need to do is you draw a mirror image to have a kind of a. You kind of do this little mirror line here. And then you just do the same thing, right? Same thing. Maybe just get a mirror image of what you have. So do it like this. Obviously do it a lot faster than the way I'm doing it. I'm doing it really slowly right now, but trying to make sure that this actually works. I've realized I've now run out of space on this side here, but you have more space in the actual thing, in the actual exam. All you need to do is just one example above the plane, one below the plane, and then the other two can be on the same plane, right? But now I've done it. Look, I've drawn a dotted line on and that represents the mirror line, right? And you should now have two enantiomers on either side of the dotted line, so and so, and two molecules now be, these are now non-superimposable enantiomers one another, and if you get these two together, they're not the same molecule. If you actually got these two together, this flipped is not the same as this. I mean, it's not actually the same thing. You may think it's the same thing, but it's not the same thing. They are different molecules. And remember, if at any time exam, this is actually a key word here. Non-superimposable mirror image. That's a key word here. So, plane polarized light. What's plane polarized light? Optical isomers are called optical because of how they interact with polarized light. Remember, optical, when it comes to microscopes, optical is related to how it affects light. The reason why they're called optical is because they have a special feature in which they react, how they interact with plane polarized light. And that's what makes these compounds special, right? So plane polarized light. So light has a property called polarization, and if light is plane polarized, this means that all the light waves have the same polarization. So you can think of plane polarized light like the edge of the piece of paper held in the air. Right, so if I was to think of can I get a piece of paper? Think of it like this, right? So light is property called polarization. If the light is plane polarized, it means that all the light have the same polarization. So you can think of plane polarized light like the edge of a piece of paper, right? Held in the air. So it can be horizontal, it can be vertical, or anything in between, right? But you have to see the idea that the light is the same. It's all traveling at the same. They're all traveling in the same kind of plane. They're all traveling in one plane. It can be like this, but they're all traveling in one plane, right? So optical activity of enantiomers. So enantiomers will rotate plane polarized light in different directions. Light will be rotated in anti-clockwise direction by one enantiomer, and light will be rotated in anti-clockwise direction in a clockwise direction by the other enantiomer. So what this enantiomer here would do, right, is that if I fire plane polarized light at this, and let's say this enantiomer here, right, it will cause the plane polarized light. So if it hits, let's say this is the compound here, if I fire in this direction, right, it will cause the light to be rotated in, let's say this is a clockwise direction, right? Say it rotates the light in a clockwise direction. It will rotate it by a specific amount, and by a specific degree. But in this one here, since this is the optical isomer of it, it will rotate the plane polarized light. Let's say it goes in this way, in this direction. Let's just say 69 degrees. There we go, 69 degrees this way. What it'll do, if it's the optical isomer, it will do it 69 degrees, the same amount, because they're the exact same optical isomers, they'll do it in the same amount, but in the anti-clockwise direction. And this is one way of determining whether or not you have two optical isomers. This is the test that you do. The test that you do is that you fire plane polarized. If you want to say, how do you know that those two are the enantiomers of one another, so the same structural formula but different ratio of atom space of the same compound, right? You fire plane polarized light. If the plane polarized light is rotated, the plane polarized light will rotate the light in equally opposing directions. That's the keyword they're looking for. Equally opposing directions, equal angle but equally opposing directions. And if so, that means that those two are enantiomers of one another. So there's something that you can get is called race mates, right? So as this is what I said before, like, so if you get a question that asks you if you've got optical activity, be careful, because certain reactions can produce an equal concentration or equal amount of both enantiomer in the same beaker or the same test tube, whatever. So be careful of that, because some reactions can produce one specific enantiomer, others will produce an equal mixture of enantiomers. An equal mixture of enantiomers is called a racemate or racemate mixture. Racemates are optically inactive because the different optical activities of each enantiomer exactly cancel each other out. So with this example here, I'm assuming that these enantiomers are in separate test tubes or in separate beakers. So we're firing a plain polarized light at this beaker of just this one enantiomer. So it's a beaker of just this one enantiomer, and it causes the plain polarized light to be rotated in that particular direction. And the same with this, right? And if we know if we did this with separate test tubes, we can then say, okay, fine, we can clearly see the rotation. These two are enantiomers of each other. However, if you're doing a reaction, you're producing the enantiomers. Producing enantiomers will produce the both enantiomers equally in the same test tube. And if these are in the same test tube, right, they cancel out their optical activity. So if you wanted to find out, if they asked you how do you prove that these two are, or that you have a racemic mixture, or why is there no optical activity, one of the things that they may ask you to say is to what they want you to say, right? One of the things that they want you to say is to say that if I was to fire plain polarized light, there'll be no overall rotation. The light won't be rotated. It will just stay in that exact same plane. There'll be no overall rotation. It will just be dispersed. I wouldn't probably say the same direction. It'll probably be dispersed. So there's no obvious equal rotation to the right or to the left. And that's because there's the same number of enantiomers of both compounds. So we don't classify racemic mixtures as being optically active, or we classify them as being optically inactive. So for example, if I had this compound here, right, and it was, let's say a chiral molecule X rotates the plane of plane polarized light by 67.89 degrees, what would be the chiral molecule? What would be the chiral, by how much? I should have finished the rest of this question, right? Let me write it down here for you. By how much? What's the angle of rotation of plane polarized light for the enantiomer? Great. So try and answer this question here. So a chiral molecule X rotates plane polarized light by 67.89 degrees. What is the angle of rotation of plane polarized light for the enantiomer? This isn't now. I'm gonna assume that you've paused the video now and you've answered this question, right? But one thing you need to understand is this is not a question that you'll get in your exam. So don't get freaked out by saying, "Oh, I didn't know what you have to do." It's a simple question anyway, so it won't really freak you out. But this doesn't come up in the exam. But the reason why I'm trying to tell you is that you understand that this would be the literal exact. This is it's understanding what's going on here, why we use plain polarized light. Why is it what's it trying to represent? All we're saying is that everything about this topic is about the fact that they're the same structure formula, different arrangement of atom space. They're exactly the same, but they just flip, they're opposite. And so this, if the answer to this question is minus 67.89 degrees. So if it's 67.89 degrees to your right, it will be 69.89 degrees to your left. Or if we're doing it on a bearing, right? If we're doing it on a bearing, and that's probably the one that I had to use, 360 minus 67.89, that's what? 293 point... 293.11. Yes, 293.11 degrees. And that would be the angle of rotation. And that's it. Hopefully this video was helpful. And hopefully this video is much better than the last one.